So not gonna lie, this is one of my favorite days of the year. We're gonna do a little bit of a activity called I Stream, You Stream. And to do that, we're gonna use the Ritz River. Yep, I'm that bad. I named the river after myself. But oh, you caught that, and it flows into MRD Lake. None of you guys don't know MRD. He's Mr. D. He's in my room for a couple of classes as well. He's another one of the earth science teachers. So yes, I do shamelessly name stuff after myself. But anyway, so also very hilariously, I stream, you stream, get it? Yeah, right? Ha! Sorry. Can't help myself when I'm that funny. But anyway, so here's what we're going to be doing. So you remember 2 days ago when we were talking about how water flowing around a meander in a river, that the water will erode and do deposition differently depending on where in the river we're talking about. So I'm just going to go ahead and read the top of page 24. I stream, you stream. So the introduction, it says running water is the primary agent of erosion on Earth. Most running water is found in streams or rivers. There are a number of factors that affect the movement of sediment in a stream. Any running water forms a stream. Gradient, discharge, and channel shape influence a stream's velocity and erosion and deposition of sediments. Sediments transported by a stream tend to become rounded as a result of abrasion. Stream features include V-shaped valleys, deltas, floodplains, and meanders. A watershed is the area drained by a stream and its tributaries. So for today's activity, which starts there at part 1, the first thing we're going to be doing is calculating gradient. You guys remember gradient? Okay, that was a chapter 2 thing. Back when we were doing connect the dots for slightly older kids. It was math. So you got that, calculate gradient. So what do we know about math in this class? You don't like it? Yeah, me neither. Do you have to memorize formulas? I guess is what I was getting at. No, you never have to remember formulas in my class. This is not a math class. And none of our math is overly difficult. But if you recall, on the front page of our reference table is the formula for gradient. So it's gradient equals change in field value divided by distance. So first of all, do you guys remember what change in field value means? I know this was from forever ago. Not a single one of you remember change in field value? Yeah, it's the change in whatever is being measured. So in this case, since we're going to be talking about elevation, it's going to be the change in elevation. If it was a temperature map, we do the change in temperature. So we're going to be calculating basically the slope of the Ritz River. So starting there at stream velocity. The average velocity or speed of a stream depends on stream discharge and gradient. Stream discharge is the amount of water in a stream. Sorry, I lost my place. Stream discharge is the volume of water in the stream. Gradient is the steepness of the slope down which the stream is flowing. There is a direct relationship between discharge and or gradient and the velocity of the stream. As either discharge or gradient increases, the velocity of the stream increases. A typical stream may vary greatly in slope between its source, which is the head, and its mouth, where it empties into an ocean or a lake or an ocean. Therefore, it may flow at different speeds in different places. At times, near the mouth of a river where the slope is small, the velocity may still be great if the discharge is great. So given the data table below, we need to calculate the gradient between the indicated points. For all calculations, we're going to use the scale. Actually, we don't have to worry about that because I gave you a scale on your reference table. So I should, on here, we're going to get rid of for all calculations, use the scale of. We don't need to do that because we have a scale on the map that you were supposed to pick up. So first things first, let's see if we can remember how to calculate gradient. So there is a spot to put the formula. I realize it's probably too small to write in there. But again, what was the formula from the front page of your reference table? So it's the change in field value divided by distance. So I just wrote change in FV field value. It's just really the change in elevation. So on our river, you should notice that I have labeled a few spots. I've labeled A, B, C, D, and E, along with directly on the other side of the river, A prime, B prime, C prime, D prime, and E prime. So the first one here says calculate the gradients between B and D. And I gave you the, oh, I don't know why this gradient, that should be formula for gradient. Geez. Apparently when I hit print this week, it did not work. But anyway, I gave you the elevation at those different locations. And this first one asks you want to calculate the gradient between B and D. So according to this, the elevation at B is 427 meters. And the elevation at D, and again, I'm just getting this right off of this chart, elevation at D is 218 meters. So we need to calculate the gradient between those two spots. So to do this, I always like to start with the formula. So gradient equals change over distance. How do I figure out how much it changes from location B to location D? We got to subtract. So you're going to take the 427 for B minus 218. That's going to be the change. How do I figure out distance on the river? What'd you say? Got to use the scale. So I have a couple of questions. So hopefully you guys remember how to use the scale to find distance. So you probably are going to need some random scrap sheet of paper. I did not ask you to get one of those out. I should have. You could just use the edge of anything, or if you still have a scrap paper from a couple when we were doing earthquakes, whatever works for you, just any sheet of paper will work. We're not going to do a big thing. But here, I got a question. We're calculating distance from B to D on a river. How do we do that? Because I want to know the distance, or really how long it is, how many kilometers it is from B to D on the river. What do you notice about this river from B to D? There's a curve. So how the water works is the water isn't just going to go a straight path from B to D. So we have to figure out how to best estimate the distance from B to D the way the water would actually flow. So to do that, we kind of have to follow the curve as best we can. Now, the best way to do this would be with something that could actually bend. For example, this piece of string I have here. Well, this would be a great way to measure the distance, because I could put it right on there and curve it up and show, okay, it's that long. But do you guys have a piece of string? Do you think you're going to be given a piece of string on the Regents? No. So you do have to estimate the best you can with a scrap sheet of paper. So here's how I recommend doing it. Just start off on your paper, and we're going to go from B to C first. I'm going to label B and C. Now what do I got to do to get over to D? Yep. And you're going to have to turn your paper a little bit. So leave C where it was and mark off D. Now, can I just show you how much longer of a path that would have been than if we just went straight across B? So then we just take this to the scale, and mine looks like maybe 6.5. Yours might be slightly different, but do you guys agree somewhere around 6.5 kilometers? Okay, so that's the distance, 6.5 kilometers. Then you go ahead and you can plug this into your calculator. I forgot to have you grab a calculator. So again, if you just want to grab your phone, that works for me. So first thing we have to do is subtract 427 minus 218 equals 209. Divided by our distance of 6.5 kilometers. Divided by 6.5. And I get 32.15. I'll tell you, in earth science, we always round to the nearest 10th unless they tell you otherwise. Which number is the 10th place? The 1. Does the 1 stay the same or round up? Round up, 32.2. And what are the units? Not just meters. Look at right here. Here's the units that we were given. The top numbers in meters, the bottom numbers in kilometers. So hopefully you remember, this is in meters per kilometer. So what this slope means is this river changes 32.2 meters every kilometer you go down this river. From B to D, that is. Now let's have you guys go ahead and do between E. I don't know, this is just between A and E. Again, just not the A to E prime. So I want you guys to go ahead and calculate the gradient between A and E. Okay, we can come around and see how you're doing with the calculation. We're all gonna have slightly different measurements for how long the river is, because that is just a way of estimating. It's the best we can do. Way better than this. Oh. 32, 37. Yeah. You're stuff. Is it really 12? You show me how to do it. I'm not seeing 12. And that we go. Yeah, I think we're getting this. Okay. So this should be just review from the beginning of the school year. Yeah, as a distance on the bottom. It was just that kind of work. We see that. Maybe that works out the one there, because I don't think that. Okay, that's 8. Yeah. No. 9, 10. Okay. All right, so what'd you get? Okay, you should have got 10.
Oh, that's what I found your treasure maps.
Oh, thank you. The Ritz rivers that flow into MRD Lake. You like that?
I saw it.
Okay, so that's 8.
No,
So now you just, oh, there's 8,
I know.
9, 10. That's almost 11 right there. So you can't just ask. All right. Let's just make sure. I think I checked on almost everybody. With measuring this. So again, you did have to go from A to B to C. Then I turned my paper to D to up to E. So that was mine. Now, when I got down to the scale, I discovered that the scale was too short. So if you see what I did here is I started and I marked off where 8 was. A lot of you realize then if we start back over, so instead where that was 8, I'm going to mark that at the 0. So this is now 8 kilometers, 9, 10, and I was just short of 11. A lot of you marked down 11. That was perfectly fine. So we have a change in field value. So 506, 500 minus 106 gave us 394 meters. And I did mine over 10.7 kilometers, which gave me 36.8 meters per kilometer. None of yours, I think, were exactly the same as mine. But as long as they were in that range, you're good. Okay, now for my favorite part. We're going to be drawing what the cross section of this river would look like. So what I want you to imagine is if I could take a giant sword and cut from A to A prime, and then you're going to be looking at that cut straight on. So we are going to be drawing what the river actually looks like. I'll show you what I mean. So it says drawing cross sections on page 25. Channels, shape, and velocity. The position of maximum velocity in a stream cross section varies with changes in the direction of stream flow. The velocity of the stream is generally greatest just beneath the surface near the center of the channel, where there is less frictions for the bank or from the banks of the river and the atmosphere. Water near and outside of a curve has its greatest velocity than water. Oh my gosh. Water near the outside of a curve has a greater velocity than water near the inside of a curve. Therefore, erosion takes place on the outside of a curve and deposition on the inside. On this stream cross section, 5 cross sections are marked. In the boxes below, we're going to draw what it might look like. Are the bottoms even? Is one side deeper than the other? So here's what I'd like you to picture. I would like you to picture that we are going to hop in this river and we're going to walk across from A to A prime. And we're going to draw what the bottom of this river would look like, what shape it is. So first things first, we got to think back to what we did on Tuesday. Where's the water going to be going faster, at A or A prime? Why? Okay, right. So if you recall, if you think about a water slide, if this was a water slide and you were headed into this curve, you'd end up hitting right here at A prime. This is what we call the outside of a curve. And remember, from Tuesday on the outside, it's going to move faster. What else is true? Because it's moving faster, what's going to happen to that side of the river? It's going to get eroded. So this side, we're going to have erosion. And because we have erosion, what do we know about the deepness of the area? It's going to be deeper on that side of the river. The opposite is all true for the inside of a curve. So on the inside, because the water is going faster on the outside, the inside is going to be slower. And when it's moving slower, we're going to have more deposition. And because we have things being dropped off in deposition, it's going to be shallower. So can you imagine walking into the river at A? What could you describe about your trip from A to A prime? It does get deeper. Where is it going to be the deepest? It's not going to be in the middle. Over on the curve. So we're going to be showing that in these boxes. So what I want you to understand is that up here, this is where you would be standing to hop in the river. That's where we're starting at A. So up at the surface. And like you guys described, it's going to start to get deeper, but where is it going to be deepest? It's going to be deepest slightly towards A prime. So I like to label the deepest spot with a dot. Now, why is it deeper over by A prime? Because it's got the most erosion because the water's going faster there. So all we have to do is just decide where the water's going to be deepest, mark it with a dot, and then connect up as if I was walking to the deepest spot. And then once I hit the deepest spot, I'm going to start to walk back up the other side. So what this is supposed to be representing is the side view of that stream where I cut it in half. This will show you that it's a nice gentle slope until you get to the deepest spot, and then a steeper slope on the outside of the curve. Let's talk about how this is going to be different at B to B prime. What do you notice about B to B prime? What do you mean they're kind of the same? Yes, it's not a curve. Yeah, it's not a curve now. So now we're on a straightaway. So if you were in this area, you're not turning, you're just going straight. Because it's not a curve, where is the deepest spot going to be on a straightaway? The middle. Straightaways, the deepest spot is going to be in the dead smack center. Do your best to put that deepest spot in the dead smack center. I know it'll probably not be perfect, but the deepest spot's in the center. So just like with the other ones, we got to connect that up. If we were to hop in, this would be a perfect V-shaped river. Now, is this exactly what the river looks like? No. But the key is we need to what I need to see from you is where the deepest spot is. Try C to C prime on your own right now. So see if you can do a drawing for C to C prime. So which one's the outside, C or C prime? C this time is the outside. C prime is the inside. So what's that mean? Where's the deepest spot going to be closest to? This time, the deeper part's going to be over near C. So you mark that with a dot, connect them up, and you've got what the cross section of a stream would look like. The deepest spot on a curve is always closer to the outside of the curve. Go ahead and do D and E. Take a look at the river. Ask yourself, is it a curve? If it is a curve, which one's the outside? No, where's the deepest spot? Easy enough? Now, we do need to do these exaggerated, like I was saying, these are not exactly what the stream would look like, but you're showing me that you understand the concept that the deepest spot is always closest to the outside of a curve or in the middle of a straightaway. No, E to E prime is not straight. You know that's on the curve. I don't think it's the C prime. Okay, I need that. Okay, so there, C to P prime is the further straight. Yep, so which one's the outside? I think that before you draw, that's the. Which one's the outside, so here's. Okay, and so where is the deepest spot? Yeah, deepest spot is the outside. Over here, you got this. Yeah, that's it. Why? Because we're looking at. So we're not drawing, this is the overhead view of it. What we're doing is if I cut this right here and then making that. So almost like when we're drawing profiles of a map, you're doing side view. That's what we're doing here. Does that actually make sense? Okay. All right, let's see. Was D curve or straightaway? It is a straightaway. Now, one thing that I know has confused people is, well, how is it straight? It's kind of diagonal up. What I need you to picture is if you were on a floaty or this was a water slide, your body would be going straight through this section. Whereas when you get to E and E prime, that's where if you're on a floaty, you'd be turning there. So that's one thing that's a little weird. And then what we're drawing. Do you guys remember back when we did the side view of the hill? The profiles? Back in chapter 2? Okay, that's what we're doing here. We're doing the side view of what the floor of this river would look like. So I'm gonna cut it from D to D prime and then look at that cut right straight with my eyes so I can see what's happening. So D to D prime is a straightaway. So in a straightaway, the center is the deepest spot connected up. It's going to look like a V. Now, I think you can tell that my dot wasn't in the dead smack center. And that's okay, as long as if you mean it to be off to the side, it's really, really off to the side. So even though mine is a little bit off to the side, it's okay because when I really want it to off to the side, it's way, way over. E to E prime, which one's the outside? E prime, so which one's the deepest? E prime. Perfect. All right, one last concept here is, in 1 or 2 sentences, explain how the shape would be different if the gradient were changed. What would it look like if the gradient was doubled or if the gradient was cut in half? How would this river change? How would the bottom of it you got it, Sean. In fact, we haven't even talked about this yet, so we'll actually hold off on that. So I just wanted to make sure you guys were able to draw them. Now, why this is important is because streams change over their lifetime. Oh, don't back up. We still got lots to go. Streams change in their lifetime, and I'd like you to go ahead and turn to page 20. Streams age just like people. We start off with youthful streams that then get mature, and then they turn into old age streams. And streams behave a lot like people. So how are young people like you guys different than old-ish people like me? Be nice, by the way. Okay, you're younger. First of all, you haven't been around as much. No wrinkles. That's where I'm going with this. And how much energy do most of you have compared to us old people? You should have a lot more. Some of you might disagree with that. So, but that is exactly how streams work. When they're young, so when they haven't been around very long, they have no wrinkles, meaning they're nice and straight, not curvy and bendy. When they are younger, they have more energy when they get to old grandma age. And so streams are just like people. So right here on page 20, we just need to get those notes and a quick picture. It's okay, I promise it's real quick. Oh no, except there's the youthful one. So a youthful stream, just like you youths, they have high energy. Page 20, sorry, I know we're jumping ahead. High energy, fast moving, steep slopes, lots of erosion. This is when those V-shaped valleys are created. So like I was saying, not a huge amount of thinking here, as long as you think of rivers like people. Kids have high energy. They're faster moving. Now, when I say steep slopes, I guess that's not really true with kids. Okay. Nice and straight, lots of erosion. This is where those U-shaped valleys or V-shaped valleys. Oh, don't think U. What does make a U-shaped valley? Glaciers. Rivers make V-shaped valleys. I figure that's really easy to remember because rivers are I-V-E-R. And you might even notice on my Ritz River paper there, I made that V nice and big so you remember. Rivers make V-shaped valleys. All right, so once they start to age, so youth is like you. I like to consider myself mature because I'm not old yet. Like I'm not grandma old. Look at me compared to my mom, we're a little different. So after youthful, you guys, comes the mature stage like me. Little more gentle gradients, starting to move slower. I still move faster than my mom, so. Side walls of the V collapse. I am not going to compare this to anything about myself because I don't want to talk about that, but just drop it, move on. Meanders start to develop. So I'm starting to get some wrinkles, but like my mom has way more than me. So I'm not there yet. Now, guys, I never mentioned what a floodplain is. Do you think you can figure it out? That's no. Put the words together. Floodplain. What do you mean by a plain? Flat area. You guys know what plains are. They're the flat lands. So these are the flat lands that get flooded by a stream. You can see this again. I know I've been talking about the Cattaraugus Creek by Kless Boys and Tim Hortons. You can see this in the whole area that is down under that bridge because there is a spot where the creek is supposed to be, but there is a spot that's nice and flat around the stream that gets flooded all the time. And nobody built their house down there because it gets flooded all the time. Any little creek you have, you'll see a spot where the stream is, and then an area that gets flooded that's nice and flat. All right, so after you're nice and mature like me, then we get even older. This is my mom. Okay, so old age, you get really bendy, lots and lots of wrinkles. I'm not old yet. 40 is not old-ish. Well, just you wait, I used to be with you. So the land is almost flat. That steep slope has basically disappeared. We get these things called oxbow lakes, and this is exactly what Sean was actually talking about when I said, oh wait, we've not gotten there yet, is because this stream is so curvy that when this water starts moving, like on a time when it would move fast, like a flood or a rainstorm,
The water source just stop moving through that certain stuff.
that's exactly it. So it's curvy here. It used to curve over here, but it didn't have enough energy to keep going that way. So it just turned and made its own path. And so that made this thing right here. It's called an oxbow lake. I think that's good enough for today. I should give you homework, but I think I'm gonna hold off. No, Nick, that's why you have an extra test.